required in your 2-page memo for the final project no later than Friday, November 14th. The sooner, the better. Why? Once a receiver, I will look at your simulation file, give you feedback immediately so we can continue to the next step. Let me tell you what's involved. This is your file number 3. First column, using dilene as a solvent, getting pure ACN product. Second column, you add an A as a feed. Because A does not contain ACN, you only send that to the second column. The goal is get 0.9992 pure TOL. The flush unit is flush all the solvent xylene to the vapor phase. And the flush temperature has a limit. More fraction, mass fraction, as siloxane and impurity in the waste stream should be less than 0.25. So you start with your file number 1, get this one, converge, get your desired product. File number 2, this is file number 3. What do you need to do? There are design variables in the column. Here are your 30 theoretical stages. You don't really need that many. Probably between 20 to 25 will be enough. Mass reflux ratio 5 could be high. You can lower that as long as you get a desired mass fraction or ACN. Why do you do that? Reflux ratio lower your condenser duty, reboiler duty. As you reduce number of tray, in this case, I have a feed location, B and C, bottom 2/3, xylene, close to the middle, 15, 12. If you lower the number of stages, you need to adjust this proportionally. Pressure, you cannot reduce that. It costs you a lot of money for vacuum. So, number of stages, mass reflux ratio, feed tray location. How about other manipulative variable that is designing input? You don't really need 200 kilograms per hour pure xylene. So you can lower this number as long as you get ACN mass fraction. In this case, 9998. The requirement is 9987. For your open loop, you should not get an ACN product with mass fraction with no safety margin, just exactly 0.9987. Once you close the loop, this mass fraction will drop. So 9987, you could get 9997, some safety margin. That's important. Okay, so now, second column. You also should lower the number of stages, possibly the reflux ratio, proportionally adjust the feed tray location. The goal is to get the TOL product 0.9992 mass fraction. Here I get 0.99949. That's good. And you come to flush unit, look at the input, you need to adjust the flush temperature, making sure you flush enough xylene to the vapor phase. Okay? And one more requirement is, look at this flush unit stream result. In the waste, look at mass fraction. Here, siloxane is only 7%. You can have up to 25% siloxane in the waste. Okay? Now, the key is you want to lower the mass flow rate of waste stream. While initially you are xylene about 200 kilograms per hour, look at the mass flow. Xylene, you are losing 30 kilograms per hour to the waste stream. If you have 140 kilograms per hour coming in, you are losing 30 kilograms per hour. That means every hour, when you close the loop, you need to buy 30 kilograms per hour of xylene solvent. You pay that continuously for 8,000 hours per year. So, this number should not be too large. It impacts you in terms of money spent to buy solvent continuously. Okay? Now, you should not close the recycle loop until you are happy with number of stages, xylene input mass flow rate, feed tray location. You get an ACN 0.9987 with some safety margin. The same thing happened to column 2. You're happy with the number of stages, feed tray location, reflux ratio. You get 0.992 plus some safety margin. And you're happy with the flush temperature. You're not losing too much xylene to the waste. Recycle enough xylene to the vapor phase. Once you're happy, you can now proceed to file number 4, close the loop. The first thing is you add an exchanger using cooling water to condense the vapor to the liquid. Look at this exchanger. Hot stream outlet vapor fraction 0, fully condensed. Your U method for condenser, I give you a heuristic handout, 0.85. For the boiler is 1.14. Liquid heat transfer 0.28. You see that heuristic set the cooling water flow rate initially, arbitrary number 50. Cooling water goes from 35 to 45. You want to minimize the cooling water flow rate, fully condense the vapor stream. That's why to determine the cooling water flow rate, there is a design spec. You can follow this example. Design spec, input, cooling water outlet temperature, CW1OT, O outlet. You look at the flow sheet. CW10 coming out. I define its temperature as CW10T. You specify this to be 45 degrees. And how do you determine how much inlet mass flow rate instead of 50? What should be the number to get this 45 degrees and also fully condense the vapor? That is this design spec. Vary. Mass flow. Cooling water coming in. CW1. Then use a mixer. Recycle